Hello guys, it's JohnnyTime and welcome to another smart contract hacking and auditing tutorial. In today's video we're solving the fourth Damn Vulnerable DeFi version 4 challenge, which is side entrance. In the video I will show you step by step how I approach the problem and how I break the side entrance contract and eventually run a successful POC and exploit to exploit the vulnerability. If you enjoy this content, make sure to subscribe to the channel, like this video, and check the other videos in this playlist with all the Damn Vulnerable DeFi version 4 solutions with Foundry. So without further ado, let's get started. At any point, if you get stuck in the exercise, check out the Damn Vulnerable DeFi version 4 solutions repository in JohnnyTime, real JohnnyTime account. Feel free to fork it, to use it, to start it. And now let's get back to the exercise. So this is the fourth exercise, side entrance. A surprisingly simple pool allows anyone to deposit ETH and withdraw it at any point of time. It has 1000 ETH in balance already and is offering free flash loans using the deposited ETH to promote their system. You start with 1 ETH in balance, pass the challenge by rescuing all ETH from the pool and depositing it in the designated recovery account. So we already understand that we have some kind of pool that people can deposit and withdraw assets, and also there is another functionality of flash loan. We have to steal all the ETH from the pool, which is 1000 ETH. So now I'm in VS Code with the Damn Vulnerable DeFi repository, and we have here this SideEntranceLenderPool contract that we need to analyze and find vulnerabilities. So we have only one import of safe transfer lib, and we have an interface of the flash loan ether receiver. We have one function execute that is external and payable. Let's take a look at the SideEntranceLenderPool state. We have the balances that maps between address to uint. Probably when people deposit money to the pool, it's being tracked here. We have a predefined error, repay failed, and 2 events, deposit and withdraw when someone deposits funds to the pool. This is the deposit function. It's an external payable function. Just essentially, people can deposit value to the contract and it's just gonna update the balances mapping. And in the end, it emits an event. So since this is Solidity version 0825, we use here the unchecked code block to prevent the built-in arithmetic overflows and other flow checks that exist since Solidity 0.8 plus. But this can never overflow because no one has such a big amount of ETH to deposit. This is just ETH. So, I mean, I cannot imagine anyone, I don't think it's even possible to have huge amount of ETH and deposits, so this will overflow. And even if it does, it's just against you because it's going to reset to a lower number. By the way, if you want to learn more about arithmetic overflows and underflows vulnerabilities, we have a whole chapter in the Smart Contract Hacking course. We have the withdraw function as well that allows users to withdraw their balance. So we check the balance of the message sender, then we delete all its balance. So we cannot tell the contract, hey, we want to withdraw only $100. If we withdraw all the balance. In the deposit, we can control the message value, the ETH that we send to the function, but in the withdrawal, we have to withdraw everything. We don't pass the amount that we want to withdraw. We delete the storage here, emit a withdraw event, and then transfer the ETH to the sender. And then we have this flash loan functionality that receives an amount, also an external function. It checks the balance before of this contract. It calls this flash loan receiver contract, the execute function. So the one who requests the flash loan, he needs to implement this execute function, right? So we called message sender this execute function, and then we pass the value, the amount that he requested in the flash loan. So we're essentially giving him an ETH flash loan without any data. And in this callback, he needs to pay back the ETH. Otherwise, this condition will be true because the balance before is lower than the balance after. So if he did not return the ETH, then we will revert the transaction with repay failed. So it's a pretty simple contract, pretty straightforward: deposit, withdraw, and flash loan. Now, how the hell are we going to exploit it and drain the pool? So one direction could be overflow here, but this is not really a vulnerability. It's not exploitable. So in order to withdraw money from the contract, we have to deposit because we need to change the balances mapping. And in the flash loan function, it doesn't seem that we can just request a flash loan and not return it, because if we will do so, the transaction will be reverted because the contract checks it over here. Now, in the previous challenge, we had this open call vulnerability where we can make the pool call any other contract, and we made it call the ERC20 contract to approve us to spend the tokens. But in that case, it's not possible because the pool specifically call the message sender, the user that requested the flash loan, and specifically this execute function. So it limits our possibilities. So it doesn't seem like we have any vulnerabilities that we had in the previous exercise, but there is something new here that we need to think wisely and exploit. And I'm going to reveal the vulnerability. So it involves multiple functions. The vulnerability happens when you combine the flash loan together with the deposit function. So in the flash loan function, you request a flash loan of whatever amount that you want, then the contract gives you this amount of ETH and execute this callback function, and then it checks that the balance is not smaller, not lower than what it was before. So you cannot really steal the ETH. You have to return it, but you can just return it, or you can go through the deposit function. So in this callback that you implement and you get to run your own code, instead of just returning the ETH by just sending it back with this low-level call or whatsoever to the pool, you can just call this deposit payable function, and that way you return the ETH, but you also tell the pool, hey, I deposited some money over here and you're the message sender, and it's gonna update the balances mapping with this value. So you're just gonna flash loan the whole amount of the ETH that the pool has, call in the callback function, the deposit function. The pool at the end, after this execution and after the deposit, it will have the right balance, so it won't revert, it won't get into this if condition, but you updated the state. So you manipulated the state, and now the pool thinks that you possess all this amount, even though it's not your capital, but it's a capital that you borrowed for a slight moment from the flash loan. And this is very, very common attack when it comes to flash loan attacks, which we cover in the smart contract hacking course. So feel free to check it out. And this is pretty genius because it's not just one function is vulnerable, but when you combine these two functions and the way the contract works, you're able to exploit it. So let's head over to the test file, and we can see that the unsolved condition is that the pool balance is 0 and that the recovery balance is all the amount of the pool, which is 1000 ETH. So this is the test, and you can see already here my exploit. So I created a new side entrance exploiter contract that receives a pool and recovery account, and this is the exploiter. And then I call this start attack function to trigger the attack actions that will make this exploit possible and eventually get this desired state where the pool is empty and the recovery is full. So let's head over to the side entrance exploiter contract and see how it works. So it's pretty straightforward, a contract that's just going to exploit the vulnerability that we discussed over here. So it has the pool and the recovery account in state, and it set them upon construction. And here we have the flash loan attack. This is the start attack that we call from the test. So essentially, we request a flash loan with all the pool balance, okay? Now, this is a bit tricky. The next line that will be executed is not the withdraw function, but we jump to the flash loan function in the pool. So the pool receives this request, and it essentially calls us back with all the ETH. So the next thing that will be executed is this execute function in our attacker contract that receives the ETH. And this is the execute function. This is the callback. It needs to be payable because we are expecting ETH from the flash loan. And then what do we do with this ETH? We just deposit into the pool using the deposit function. So we are paying it back to the pool, but we're going through the deposit function right here. Now this will finish, and then we are back here, right? This callback finished, and this will be false because we returned all the ETH to the pool through this deposit function. So this revert won't happen, and we will successfully complete the execution of the flash loan function. Now we're back to our attacker, and now that the flash loan is completed, we can call the pool.withdraw that we already saw that it's just gonna withdraw all the funds, all the balances of our account, and it's gonna send us all the ETH. And we need to create another payable receive function because we are the ones that are gonna receive the ETH that we just stole using the flash loan and deposit functionality, and we need eventually to transfer it to the recovery account. So this is a beautiful attack actions, and I'm gonna go through it again. So we have the constructor that just set the state, the start attack, it starts the flash loan. After the flash loan, during the flash loan, we receive the callback with the ETH here. We deposit all the ETH into the pool while increasing our balance in the balances mapping. And after the flash loan is completed, we're back here. We call this withdraw function to withdraw all the ETH that the pool thinks that we have because we just manipulated the balances mapping. Then we receive the ETH over here in the fallback receive payable function and transfer all the ETH to the recovery account. And after everything, this state's supposed to be true. So let's check it out, shall we? We're gonna go to the terminal and we're gonna do forge test. This time we're gonna run here side entrance. No need the verbose mode, just run the test and succeeded. We were able to pass this test side entrance test, which means that we broke the contract and got the desired state. Congratulations, you completed the 4th Damn Vulnerable DeFi version 4 challenge with Foundry. And if you enjoy this content, make sure to like this video, subscribe to the channel, and learn smart contract hacking with me. Thank you so much, and I will see you in the next lecture.